This video will help you solve some of the problems in page 79 and 80. So in here we have a box on a floor and it's been pulled at an angle. So this angle is, in this scenario, it's 40 degrees. So if I want to do a free body diagram, I draw a circle around it. And so it's touching this surface, so there's going to be a reaction or normal force perpendicular to the surface. And also it's touching the rope, so there's a tension along there in that direction. So these two forces are contact forces. And now we're going to look at non-contact force. So there's one non-contact force, it's G traveling downwards. And this force is equal to this. Even though the arrows are different size, I should have made them both equal size. Also, this scenario only applies if this surface has no friction. So you can think of it as maybe it's on a piece of ice, but if there's friction, there'll be another force going that way. So that'll be a contact force as well. The friction caused by the contact between the ground and the bottom part of the block. And also these small arrows on top of these are just to show that these are vector quantities, so that there is size as well as magnitude. So the size here are given by the size of the arrows. So if I draw two arrows the same length, that means that the magnitude are the same. So this force will have vertical and horizontal components as well. So let's look at how we're going to calculate those. So the vertical component will be 20 sine 40, and the horizontal component of that tension will be 20 cos 40. No, we're not including friction in this case because we assume this is on an ice or a frictionless surface to make things a little bit simpler. So mass of this block can be worked out by m times 9.81. So that gives you that force here. Okay, so let's put things together. So let's look at the horizontal. So horizontally you got your R, that's the reaction force, plus there's a vertical component from that 20 newtons. And since there's no acceleration in that direction, that must equal to G. So this we can work out by 20 sine 40. R is the thing that we need to calculate, and G is mass of the block times 9.81. So in horizontal direction, there is no other force except a component of this. So you got the 20 newtons, and so the horizontal will be 20 cos 40. So there's a net force in that direction, up this way. Okay, so this is the same picture on page 80. So you have the slope on 25 degrees and the block is here. And there's a force at 140 newtons. So you can think of someone pushing in that direction. And we're already given 820 newtons in that direction. So if we want to find a component of this force along this slope, we can do that by knowing that this angle must be equal to this angle, because if you have two parallel lines and it's another line bisecting it, alternative angles are equal. So this angle is 25 degrees. So the component of this force along here will be 540 cos 25 in that direction. So if you want to look at the component of this force acting in this direction. So if you draw it into a triangle, that angle will be 65 degrees, because sum of all three angles adds up to 180 degrees in a right angle triangle. So 820 is downwards, and if we want to find the component along this surface, and you know this is 65, so it becomes 820 cos 65. So now you have found B. So the B is a component of the 820 newtons. We want to find the net force. So the net force from this and this. So when you take away one from another, so the net force is that minus this, which means there's an overall force acting in that direction. And if you get the A minus B wrong instead of B minus A, you just get a negative, which pretty much tells you that the force is the other way.